yesterday we were talking about the AdS3 CFT2 examples. We first described the Vassiliev theories in AdS3, which were relatively simple, based on a Chern-Simons-like formulation for the higher spin gauge fields coupled to a scalar, but there was a one-parameter family of such theories which labels both the symmetry algebra as well as features like the mass. So that was the only parameter in the theory. So that was the bulk picture, the bulk set of theories we are interested in. The proposed dual was to a class of two-dimensional conformal field theories, which I began to describe as well. And these are also a very natural class of two-dimensional theories, these so-called Coset models based on SUN. The unusual thing was to take a 't Hooft-like limit in this model, which gave rise to parameter lambda once again, which in the Coset model was n over n plus k, the k being the level of the coset. So this parameter lambda, of course, the proposal was to, after identifying these two parameters lambda between the bulk and the boundary theories, that there's an exact holographic duality. So I was in the middle of describing this Coset theory. So let me just remind you very briefly. So the theories were these SUN level k. So there were these Coset theories, which are the WN minimal models with this discrete set of central charges, which included the Virasoro discrete theories. And one important fact, which will be important, is the fact that you know completely the spectrum of all the states in the theory. That's the remarkable thing about two-dimensional conformal field theories. Unlike in many of the higher dimensional cases, I mean, in four-dimensional n equal to 4 Yang-Mills theory, people have been struggling for years, and now finally in the planar limit, we know something about, we know in a somewhat implicit way the spectrum of all the single trace operators, but in two-dimensional conformal field theories, the spectrum is, known very explicitly, and here I have it written for you. The conformal dimensions, rather this is the left dimension and there's a corresponding h bar. The conformal dimension is the sum of the two. But the primaries themselves, the spectrum, it's labeled by two representations of SUN, and it reduces to familiar expressions. And moreover, you know the full partition function of these theories, in the sense that if you consider this two-dimensional conformal field theory on a two-dimensional torus, so if you wish a finite temperature theory, then you can write down the partition function. So Q is essentially e to the 2 pi I tau. The real and imaginary parts of tau are the temperature and the chemical potential for angular momentum. So the CFT partition function is also explicitly known. So namely, you know the primaries. I should stress over here that when I say primaries over here, these are primaries with respect to in this particular case, with respect to the Wn symmetry algebra. So normally in two-dimensional conformal field theories, you talk of primaries with respect to the Virasoro algebra. So you have a primary, then you have its so-called Virasoro descendants, which are essentially derivatives and action of the higher Virasoro modes on them. But since this theory has a larger symmetry algebra than the Virasoro algebra, namely this Wn symmetry algebra, we label the states by the Wn primaries, and we need to know for a given Wn primary, what is the structure of the states above it, or its descendants, and that's captured by these branching functions, which effectively encode information about all the null vectors that are present, etc. And it's given by a fairly explicit formula, which generalizes that of the Virasoro minimal models, where those of you who know about the Virasoro minimal models know that there's a very intricate set of null vectors and so on. So this is a generalization of that to the SUN case, and it's given in terms of things which are mathematically well defined. The sum over this affine Weil group, which consists of sort of translations and anyway, I won't have time to explain that, but it's well-defined mathematical object, and this partition function that I wrote down is so this was, if you wish, for the left moving side, and then I combined it with the right moving side, the q bar, and took mod square and the sum over all the primary, the contribution. This is modular invariant partition function in the sense that it's invariant under the more general SL2Z transformations on tau. There are other modular invariant combinations which one can construct which don't involve necessarily taking such a diagonal combination. Namely, you can put together different sets of primaries from the left and right and form a modular invariant partition function that also would give you a consistent two-dimensional CFT. What its bulk dual is an interesting question, and I think no one has addressed that. So in any case, we will stick to this diagonal modular invariant partition function. I want to say a little bit about the Wn symmetry. Since I don't have very much time, I'll be a little sketchy, but if you want a very quick and to the point introduction to it, just look at Polchinski's volume 2. He has a small subsection on the Wn symmetry in one of those later chapters which people never get to on advanced conformal field theory. But it's a very succinct description of what the Wn symmetry is. So you know, of course, that there's a stress tensor whose modes are the Virasoro generators. But here there are, as I mentioned, higher spin conserved currents. There's W3 and so on up to some Wn in the case of Wn symmetry. How these are constructed, at least in this Coset models, one explicit way to construct them, these currents, is to exploit the fact that in the Coset theory you can, so let's take n equal to 3 case, the first non-trivial case. So that's based on an SU3 Coset theory. In SU3, you know that in addition to the quadratic invariant, Casimir invariant, which actually determines how the stress tensor is constructed, the stress tensor is constructed as summation JA, which you can think of as the quadratic Casimir. So in a West-Zumino-Witten theory, for instance, this is the Sugawara construction of the stress tensor. So if you wish, you can think of this as, these A's are Lie algebra indices, so you can think of this as the built from the quadratic Casimir, but when you go to SU3, you have higher order Casimir invariants, like a cubic Casimir. So, and now we are considering, remember, a G mod H theory where G is SUN times SUN, with one of the SUNs being at level K and the other at level 1. So I'll call the corresponding currents JA 1 and 2. These are both the terms in the numerator of the coset. Let me just consider an arbitrary combination, a cubic combination of these currents, J1 and J2. So this is the most general linear combination of cubic combination. So either with 3 1s or 2 1s and 1 2, or 2 2s and 1 1, all 3 2s. So consider some object like this. And if you demand that this has a vanishing OPE with the diagonal SU2 current, the SU3 current, which is JA1 plus JA2, which is generated by, this is the diagonal piece, which is what you mod out by in the coset. So if you demand that this combination of currents has a vanishing OPE with this, that gives you actually some conditions on A1, A2, A3, and A4, and you realize that there are always enough equations to determine the unknowns up to, of course, an overall factor, which is irrelevant. So there are 3 unknowns here, and you get exactly as many equations. So there exists a spin 3 current in this theory, a holomorphic current in this theory. And similarly, for the higher for the higher SUNs, there are as many as n or nth order Casimir invariants in a SUN theory. So SU3 theory has up to cubic, SU4 quartic, and so on. So you can generate in a similar way these higher spin conserved currents. But if you consider the algebra of these, so the OPE of these two, or the commutator of 2 of these, you get a nonlinear symmetry algebra, which has quadratic terms in these currents on the other side. So it's not a Lie algebra, which is what makes many of its properties very difficult, and why people were very scared of them even in the old days. But nevertheless, okay, there's something about RG flows in these theories, which I think I won't have time to talk about. So that was a quick survey of this Coset model. So now we want to do, as I said, something a little unusual, which is to take the Stoft limit. It's not at all obvious because, as you see from this construction, it's not based on some vector model or any n-component vector or anything like that. So it's not obvious that there is a Stoft limit in the standard way. But let's go ahead and see what happens if we nevertheless decide to do something like take n to infinity and the k, the level to infinity, keeping this combination fixed. So the first thing you notice is that the central charge has a nice limit. From the expression we had a couple of slides ago, you can see this was the expression for the central charge. If I take n over n plus n over k plus n to be fixed, which as lambda, then this is lambda. The 1 can be dropped in the large n limit, so this is also lambda. So it's lambda square. N minus 1 is essentially n. So the central charge goes like n into 1 minus lambda square. So it's growing large, but the nice thing is that it seems to grow like n. So it's like a vector. The number of degrees of freedom are like that of a vector model. So okay, so that's something encouraging. Now let's look at the dimensions of some of the operators of the primaries. So the simplest primaries, as I said, you label primaries by 2 representations. The simplest labels are where you take the simplest representations anyone knows about SUN is, of course, the trivial representation. So you take lambda plus to be the trivial representation and lambda minus to be the fundamental. Well, you could take the case where both are the trivial representation, in which case if you apply the formula, you see that it's equal to 1. So that's the vacuum, that's the identity operator or the vacuum state. That's no surprise. But the first non-trivial case is where you take one of them to be the fundamental, and then there's this expression I had written down yesterday, which follows from the earlier one. But in the large n limit, this is some strange rational number, but in the large n limit, it takes a simple form, half into 1 minus lambda, as you can simply see from here. And the other operator, with lambda plus equal to fundamental and lambda minus equal to the trivial representation, again, is generically some other different rational number. And in fact, these rational numbers are the ones that determine the scaling dimensions in the Ising model, for instance. If you put n equal to 2 and k equal to 1, these give you the Ising model, some of the Ising model scaling dimensions. And so in any case, these rational numbers, in the large n limit, this one goes to half into 1 plus lambda. So whereas these two generically didn't have much of a relation, you see that in this limit, they sort of become, in fact, they add up to 1. Their dimensions add up to 1. And I mentioned that in the bulk there was a scalar field with m square equal to lambda square minus 1, with the AdS dictionary, the delta, which is equal to d by 2 plus minus m square plus d square by 4. If you put d equal to 2, then and m square equal to lambda square minus 1, you see that this is just half into 1 plus minus lambda. So the two different delta plus, delta minus just give you these two numbers. And that's very important, because if you have to think of them as scalars with opposite quantization, the sum of the dimensions delta plus plus delta minus should add up to 1, which it doesn't in general at finite n, but it does in the 't Hooft limit. Okay, in any case, the other nice encouraging thing that leads you to believe things are going well is then you look at the next non-trivial case, which is the next representation you would have, that would come to your mind, the adjoint representation. And if you look at the dimension of that, it's some other number, but in the large n limit, it's 1 minus lambda. And similarly, this one is 1 plus lambda. So they're exactly twice this. And that's encouraging, because that's what you would expect in a theory that has a good 't Hooft limit, that you would expect states to be states like the adjoint to be multi-particle states built out of the basic single particle states, which in this case we identify with the one if you have a single scalar in the bulk with this mass, then that corresponds to states, single particle states with this energy, and in the 't Hooft limit, other excitations should be multi-particle states of these. And so in the large n limit, where there are no interactions between from the bulk point of view, it's a free theory. The sum of the energies should just add up, and that's what you see over here. Identity operator, no tachyon. I mean, yeah. I mean, this mass, I mean, this is above the Brighton-Lohner-Friedman bound, so this... Oh, no, CFT is unitary, so you have 0, and then you have positive primaries with positive dimension. So yeah, it's unitary by construction because it's built from a SUN, Weismann-Witten theory. So yeah. So in general, representations which are finite tensor powers of the fundamental and anti-fundamental dimension representations like these I've written down have finite scaling dimensions. These are not all the ones that have finite scaling dimensions. There's a complication, we'll see, but all these certainly do have finite scaling dimensions. So so the large n limit at least seems to have a chance of working. There's a large, exponentially large degeneracy, actually, which is a very strange thing that happens in this limit, which is one of the unusual features of this theory. Namely, you find that there are many operators with almost the same dimension in the Stoff limit. For example, if you consider primaries labeled by lambda and lambda, by the way, I should have mentioned, if you would see from the earlier case that it's not symmetric between lambda plus and lambda minus, and there's no reason for it to be. So in any case, but if we consider the lambda primaries, you can work out their dimension by the same formula. You find this is the answer at every finite n and k, but in the Toft limit, it essentially goes like 1 over n times this number of boxes. B of lambda is the number of boxes in the Young tableau corresponding to lambda. So if the number of boxes were finite, these would seem to go to 0. The boxes were finite compared to n. As you took n to infinity, these would seem to go to 0. So you might then worry whether a good large n limit exists because you seem to have many states which are almost degenerate with the vacuum. Nevertheless, actually, correlation functions of the Wn minimal model do seem to behave well at large n. So you might at first be very worried by this because there would be, in principle, there could be many states in intermediate channels and so on, and which would spoil the large n suppression of the usual arguments for why say a 4-point function gets suppressed relative to a 3-point function, etc. But this question has been looked at very closely by two sets of people. Kyriakos, who used to be here, I guess is still here, but Subrat Raju and Shiyin and a student later, they studied various classes of, especially this paper, they did a more general analysis of the various sphere 3-point functions and showed that it demonstrates all the expected properties of the large n behavior. Essentially, the point is that even though there is this large degeneracy, it does not spoil the large n behavior because the fusion rules between these different states is very special in this CFT. So you cannot just bring two states together and form any third state. There are selection rules governing which state can be produced in the OPE of two of these operators, and the selection rules are essentially like Klebsch-Gordon selection rules for SUN representation. So if we take two representations like of SU2, you can form some finite number of representations. You cannot form arbitrary representations. So even though there's a large number of them, they won't, to any given process, only a finite number of them will contribute. So in fact, most of the light states actually exactly decouple in any correlation function, which sort of suggests that these light states, even though they're light, they're somehow non-perturbative or in a slightly different sector from the other states. And this is something, in fact, currently, I mean, maybe I'll say a little bit more later about this. So, okay, so So the 't Hooft limit, independent of anything, is an interesting new aspect to these models that I think can be studied independent of any of these dualities. But let's, at the moment, leave that aside and come back to the duality and try to, let me just quickly describe in the rest of this talk the various checks which you can sort of classify in 3 categories as matching the symmetries and the spectrum, about which I've said a little bit, about matching correlation functions between the bulk and the boundary, and something about how the properties of black holes and other solitons also in the bulk also match with things on the boundary theory. So there's a fair amount of evidence now for this proposal. So the symmetries, even the symmetries actually in this theory are very subtle. So you might think at first sight that's the simplest thing. I mean, you check and okay, you get over that and say that that's the, okay, 0th order check. But in this particular case, even the symmetries are realized in a highly non-trivial way. I mentioned to you that the result of originating, of course, from Henno-Ray and Campoleoni et al., but more generally by Matthias and Tom Hartman, that the asymptotic symmetry algebra of the bulk HS lambda Vasiliev theory has a W infinity lambda symmetry, and which seems at first sight very different from the large n limit of the Wn algebra. Why is it different? Because remember our lambda was between 0 and 1, whereas I told you that HS lambda truncates to SLN when lambda is equal to n. And it was the SLN Vasiliev theories that had a Wn algebra. So you might think you would have to take lambda equal to n going to infinity to get the large n limit of the Wn algebra, which would mean an HS lambda going to infinity limit, whereas we want lambda to be between 0 and 1 and something finite. So at first sight, it seems as if the symmetries are even very different. But actually, by now there's a lot of evidence that even the symmetries, these 2 symmetry groups which look very different, are actually identical, and it's a very non-trivial fact about these W infinity of lambda symmetries that they truncate to Wn in very non-trivial ways for different values of lambda, and there are generalized dualities. So there's a lot of evidence for this, and it can be motivated or proved depending on how you view it by thinking in conformal field theory language in terms of what is called a generalized level rank duality, which allows you to talk about cosets sort of formally by extending the level and rank to non-integer numbers. So there's some kind of a formal equivalence you can make, which so this is our Wn minimal model, but if you believe this kind of formal equivalence under this level rank duality, which exchanges this n and k for 2 other combinations, lambda and L, where lambda and L are given by this, lambda is what we define, and then this side you can argue should have a W infinity of lambda, because this is essentially the SL lambda, HS lambda or SL lambda that we talked about, and so the symmetry group of the right-hand side is the extension, as I said, of SL lambda or HS lambda, while that of the left-hand side is that of the Wn. And in fact, with Matthias now, we have even more stronger indications of the evidence of this equality at finite n and k. So the matching of the symmetries itself is quite interesting and sort of works in a very miraculous way. So given the symmetries, let's look a little bit more closely at the spectrum. I told you a little bit about the spectrum in the CFT, but we'll come back to that. But let's now look at the spectrum from the bulk point of view. The bulk has these higher spin gauge fields and two scalars, complex scalars. And what we are asking for is the question: if those are the only fields in your Vassiliev theory, then basically them and their multiparticle states should account for all the states in the CFT. That's what your AdS CFT would tell you. And if you want to match to leading order in large N, you just have to look at the linearized fluctuations. So basically look at the spectrum of oscillations around, the quadratic terms, and look at the spectrum of the theory in the bulk, and that's what gives you. That's what would give you the bulk quantity. So one way in which you can compute the bulk spectrum is to compute its partition function in a thermal background. So now we are talking of the bulk AdS3, but you put the time direction on a circle and compute trace e to the minus beta h. So that's the way you would organize the spectrum. And to compute the partition function to this leading order in large N, where you need only the free or quadratic fluctuations, you just have to compute the one loop determinant, the one loop answer in the one loop partition function in the bulk, the determinant of the quadratic operator for the fluctuations is what would give you the spectrum of all the states. And so this one loop determinant on thermal AdS3 can be computed. Of course, yeah, the partition function has a classical piece, which is the classical action in the bulk, and times the one loop piece. The one loop piece has contributions from higher spin fields and from the scalar, the two complex scalars, but they are oppositely quantized. So the delta plus and delta minus, which correspond to an H plus and H minus, which are these two values. So there are two of them. So this, you need a scalar determinant and you need higher spin determinants. So one loop determinants in thermal AdS3. And this actually turns out to be the classical action, which is more or less straightforward thing. These one-loop determinants are a bit like what you saw in Marcos's talk, where he evaluated one-loop determinants in S3. There he used some zeta function regularization. Well, in the case of higher spin fields, it's a little more technically complicated. He was looking at one-loop determinants of gauge fields, scalar fields, and fermions. But here you need one-loop determinants of Laplacians of higher spin fields. But anyway, it can be done, and the final answer is actually very nice. The complete higher spin one-loop determinant can be written as a sum over contributions from spins equal to 2 to infinity, and the contribution for a given spin S is this product from n equal to S to infinity, which can be rewritten this way. And this piece is what some people who are connoisseurs of these things know as the McMahon function, and appears in actually many context. So I'll just denote this whole thing by the m tilde of q. The scalar determinant is relatively easier, and that's given by a simple answer like that for a given h, for a given scaling dimension. But one can actually rewrite it in a slightly more suggestive way in terms of sort of characters of U infinity, sum over representations of characters of U infinity with some chemical potential related to, so this Zi are q to the I plus h minus 1, where I are integers which go from 1 to infinity. So, this this single particle. The single particle, okay, never mind the single particle's contribution. In any case, you can rewrite the full answer, the bulk answer, therefore, as this classical piece. This is the higher spin piece. And then the scalar piece from all the different scalars you can write in terms of these sort of characters. These are also sometimes called Schur polynomials. So there's a sum over representations of U infinity. And these are sort of representations with a finite number of boxes in the Young tableau. And there's a way to interpret this as the combined contribution from multi-particle states of the complex scalar with dimension h plus, with the pieces r plus, s plus, and that of the scalar with dimension s minus. These r minus, s minus pieces. And these are dressed with these so-called boundary graviton excitations with the higher spin modes. So basically, all the free excitations of the scalar field have been just put together over here. This is the generating function from which you can read off the whole. And this is this is the free Fock space of all these multi-particle states generated from these different scalars, the higher spin fields, etc. So that's the bulk perturbative answer.
The index I on the right-hand side depends on the representations.
No. Sorry, I think I should have put this in. When you write these Schur polynomials, you have to, basically you have chemical potentials in the, it's basically like a while character. So it's just the chemical potentials that you put in the Cartan of the SU or the U infinity. So I should have been a little bit more precise there, but okay, so that was in the bulk. There's a answer which looks complicated, but still is a concrete answer. But on the CFT side, the spectrum I told you was captured in terms of these branching functions, and the branching functions had this piece in terms of all these, in terms of all the sum over the affine Weil group, etc. The nice thing is that these simplify a lot. In the 't Hooft limit, you can rewrite them in various nice ways. One of the things you see is that this McMahon function comes out quite nicely, and then, or you can rewrite it in terms of other simpler branching functions using, these are things that appear, these are sort of conformal field theoretic objects, so you don't need to know the details at the moment, but basically this object that appears here is one of the simpler branching functions where you put just one of the representations to 0, so you can think of the general thing is some linear combination of these branching functions. These are just some numbers. some kind of generalized Klebsch-Gordon numbers. And these are number of boxes in the representations, etc. And these branching functions, you see, turn out to take a very similar form to what we see in the bulk. Namely, this is actually C over 24. You can already see that. This was my C that I defined, the McMahon function over here. And you get precisely the same kind of Schur polynomials or characters, but with some, if lambda can be written in terms of, I haven't given all the details of all the technical things, but lambda can be written as sort of fundamentals plus anti-fundamentals, and then you can break it up in this way. But now you have to make a choice. There are all these extra degenerate states. If you drop those extra degenerate states, which in the strict n equal to infinity level, there is a rationale for dropping them, they sort of decouple. But suppose you drop them, then it turns out that the modified answer in this linear combination over here, basically only this piece contributes, and the full answer, not the full, I mean this modified partition function dropping these states is basically this thing square, which agrees with the contribution from the perturbative excitation. So there's a part of the CFT answer which reproduces exactly all the perturbative excitations in the bulk, and the part which you've dropped are these extra degenerate states. But all the perturbative excitations are captured precisely by this. Now, another way to interpret this is actually in terms of the symmetry algebra. I mentioned that the symmetry algebra is very non-trivial between the two. So it turns out, in fact, that these objects, these basic building blocks, are essentially characters of this HS lambda symmetry group. But as I said, it's not at all obvious that the minimal model CFTs have this HS lambda symmetry, but the fact that the branching function takes the form of these HS lambda characters is another indication of the matching of the symmetries, and is needed, of course, for this part of the agreement to work. But we also need all these additional light states at finite n. So maybe at infinite n you could drop these additional light states. But at finite n, you need them all for the theory to be a modular invariant conformal field theory. And you might ask, where are these states in the bulk HS lambda theory? We had all these perturbative Vasiliev states, and they accounted for a part of the CFT spectrum. Where else can we? How else do we match the remaining states to this additional sector? A complete accounting of all these additional states has not yet been done, but there are in fact quite strong indications that these are related to certain light, non-perturbative states in the bulk theory. So they are not from the perturbative fluctuations of the higher spin fields, but they are actually solutions that you get. So in fact, there's a special class of classical solutions in the Vassiliev theory, which are not, I mean, the Vassiliev theory has, of course, the AdS3 vacuum as its solution, and then there are fluctuations of the gravitons and the higher spin-ons or whatever, and then all of them. But there are additional semi-classical solutions which are smooth. They look at first sight like singular solutions because if you look at, in a particular gauge, if you look at the geometry, they look as if they have a conical defect, but they are actually not singular geometries in the full Vassiliev theory, which is one of the indications of this third theme that I alluded to in the beginning about how these Vassiliev theories have sort of a C geometry in a different way. In this case, it's actually all very concrete and very hands-on because one can actually look at the Vassiliev theories with the SLN Chern-Simons theory. They're not quite the ones we need. The HS lambda is they're not the most general HS lambda, but SLN is a good starting point. So you look at the SLN Chern-Simons theory description of these Vassiliev models, and you know gravity sits as an SL2R subgroup of this SLNR. But the SLNR gauge group can mix the SL2 with other pieces. So that's the reflection of the fact that under this higher spin symmetry, the gravity spin 2 field mixes with the spin 3 field, which mixes with the spin 4 field. They're all mixed up together. So what was the curvature tensor, which we think of, which we are taught from childhood as the only covariant object, diffeomorphism invariant object to study, is actually not a gauge invariant quantity in a higher spin theory. So even the Ricci scalar is not a gauge invariant quantity because it would be mixed up with one of the curvatures or analogs of curvature for the higher spin field. So what might look to be singular, so where the Ricci curvature has a delta function singularity like in a conical defect, by a choice of gauge, might just go away, just like a black hole horizon is just a coordinate singularity. It's not diffeomorphism invariant. So the singularities of this kind so there are at least a class of geometries. It turns out that there's discrete values of the conical deficit angle for which it's actually smooth. So we found a large class. In fact, if you take n very large, they form a discretium of states which stretch all the way up to the vacuum. Namely, there are conical defects with arbitrarily small opening angle or deficit angle. So, I mean, in the large, if you take n very large, they are arbitrarily small. And they form a discretium. And it's interesting, in fact, that so there's a precise spectrum you can work out, and they carry higher spin charges as well. They are not vacuum solutions, so they carry charges. They have masses, of course, higher spin charges, etc. And in fact, these lambda primaries that I mentioned to earlier, which also form a discretium going to the vacuum, are related to these states. In fact, to the extent we've computed to up to spin 4 charges, it's fairly non-trivial that they agree. But we computed these conical defect geometries in the SLN Chern-Simons theory, and then you had to do a certain analytic continuation to go to the HS lambda theories that we really want to compare with the WN minimal models. But after this analytic continuation, which we now think we understand even better. They are perfectly accounted for by these novel solutions, so which raises the hope that you can account for the whole all the additional states from these extra non-perturbative states in the theory, which is a very novel feature of this this AdS3 CFT2, which I don't think any other AdS CFT example has. So, okay, so that's what I want to say about the spectrum, about correlation functions. The spectrum is essentially the information in 2-point functions, but we can compare 3-point functions, for instance, of two of these scalar fields and spin S current with the corresponding bulk 3-point function of 2 scalars and 1 spin S gauge field. This was done first in special case for certain values of S and lambda by these people, by Sheehan, generalized a little bit by Ahn, and most completely by Per Krause and his group, and who managed to match both sides for any value of the spin S and parameter lambda. So this is the expression for the 3-point function, has some fairly interesting dependence on S as well as lambda, and they were able to reproduce this from the Vasiliev, again, cubic interactions involving the scalar field and the gauge field. And the CFT, well, I should mention that these people also assumed this thing for which I mentioned there is now a lot of evidence, that the CFT has this HS lambda symmetry in the 't Hooft limit, in this sort of realized in this non-manifest way, but so it seems a reasonable assumption. But modulo that, they were able to match these 3-point functions. And finally, to come back to this theme about this geometry and stringy geometry, in the last few minutes I'll just say a little bit about black holes. Unfortunately, it looked as I didn't have time to say much more, but I'll just give you some of the conceptual highlights without writing down any formulas, which you can find in these papers. So these theories have a new class of black holes, which are generalizations of BTZ black holes, and that they carry higher spin charges. The first such solution was worked out by Gopakumar, Krause, and then in more detail by them and their students. And they originally worked with the SL3 Vasiliev theory to start with. As I mentioned, the notion of singularity is now a gauge-dependent concept, since the curvature tensor is not gauge covariant. So a solution that has a singularity may be smooth after gauge transformations. Actually said all this about singularities could possibly be gauge artifacts. They need not always be gauge artifacts. They could be gauge artifacts. So I should have maybe said that not are, but could be. So of course this was pointed out by them, and also Castro, Hirano, Maloney, and his student. So how do they? So, okay, you think, okay, they are all gauge artifacts. I mean, we've lost our Riemann tensor and our Ricci tensor, so what is the ground we stand on? Well, there are some gauge invariant quantities, at least in these Chern-Simons theories. It's fairly familiar. The SLN Chern-Simons theory, or any gauge theory, has gauge invariant quantities which are holonomies, the path-ordered exponential of the Wilson line, as you've heard from in Fernando's lectures. So these Wilson lines are, of course, you can take the trace of these Wilson line. That's obviously gauge invariant, but more generally, you can talk about the eigenvalues of this matrix. These are also gauge invariant. I'll talk more about the matrix as such, by which I mean its eigenvalues. So they are gauge invariant quantities. In Chern-Simons theory, actually they are the only gauge invariant quantities because the field strength is 0 by the equations of motion. So you cannot construct something like trace of f square, which you would do otherwise, or any other such local operators which are gauge invariant. Basically, the holonomies are the interesting objects. So you work with them, and in fact, that's what these people did, and that's what we also did when we studied the conical defects. So one way, if we have sort of, we do not have a notion of geometry and so on, what do we take as a definition of a black hole? What is a black hole in these theories? Well, one working definition could be the one they propose, which is, firstly, you can always talk about topology even if you can't talk about geometry. And Euclidean AdS3 has the topology of a disk. Let me talk of Lorentzian AdS3. Let me just talk about Euclidean theories at the moment. Take global AdS3 is sort of a disk times r, the time. So the spatial direction is sort of contractible. The disk is a contractible direction. So if you were to now go to thermal AdS3, you would make the time direction into a non-contractible circle, but the spatial direction would be contractible. On the other hand, if you looked at a black hole geometry, things are the other way around. The time direction is actually contractible. The time direction shrinks to 0. You know this probably from studying the classic Gibbons and Hawking paper, that in the Euclidean signature, the black hole is one in which the time circle sort of shrinks smoothly at the horizon. But now the spatial circle is not contractible because there's a horizon. So you can take a black hole, at least in this case, and this generalizes to higher dimensional AdSs also, as one which has this sort of topology in which the time circle is a contractible loop. And smoothness, therefore, demands that this any holonomy along this contractible circle must be trivial. Otherwise, there would be a singularity. This is a generalization of the Gibbons and Hawking kind of idea that the geometry must not have a conical singularity at the horizon. Here you don't have a horizon, but you have a gauge field and it has a holonomy, and you don't want it to be to have any singularities, so it must be trivial. So it must be some e to the. So in fact, they take the holonomies in the time direction to be the same as that for the BTZ black hole, namely for the SL3 case, which they started off, have eigenvalues which are eigenvalues of the gauge field to be 0 plus minus 2 pi I, so that it exponentiates to the identity. This actually gives two relations amongst 4 quantities. This is very similar. Let me remind you again about the Gibbons-Hawking, where the smoothness at the horizon just gives you the temperature in terms of the mass, or equivalently the mass in terms of the temperature. That's the condition that fixes m versus beta. Here they have a case where you have mass, which is the spin 2 charge, and temperature, which is its dual, thermodynamic conjugate. and then there's a W3 charge that they have, and its corresponding thermodynamic conjugate, the chemical potential. And but you get, actually, they find that demanding this holonomy in the time direction for the classical gauge field gives you two relations amongst four quantities, and those relations precisely then lead to the first law of thermodynamics, just like this relation between m and beta is what is necessary for the first law of thermodynamics for a black hole to, in fact, in this case, there's an additional integrability relation so that it follows from a partition function, which is non-trivially obtained as well. So it's a very non-geometric way of obtaining the black hole entropy, which I find very interesting. This was generalized to higher spin theory, spin 4 case, but also, most interestingly, to the W infinity of lambda case by Krauss and a student. And the partition function has was expanded. This is interesting, of course, because this is the one you can use to now compare with the CFT. The partition function agrees with the CFT answer, so the meaning it's basically the partition function for something that carries this chemical potential and energy agrees with the CFT answer. They checked it initially in a series expansion for I'll just finish. I think this is basically my last slide. So lambda equal to 0 and 1, but Matthias, Tom Hartmann, and Kiwang Jin have now, I think, in what is probably almost completed work, which shows the agreement for arbitrary lambda. So, so this from the CFT side, it's a fairly non-trivial calculation to do this at arbitrary lambda at 0 and 1, as I've mentioned. You have a free fermion, free boson description, which allowed Krauss and Perlmutter to make a fairly straightforward comparison, but for general lambda, it's quite non-trivial that it also agrees. So in any case, that's a very interesting direction. Now I have 3 slides of various questions that one can this thing, but I'll just leave that for on the web page where you can all see it, and I hope you're not been intimidated by the subject to not consider working on it. But in any case, thank you very much.
Thank you very much. Let's take some questions.
So in looking for these additional solutions that finally account for a part of the light states that you need for modular invariance, I mean, did you get some hint from these properties, the properties of these light states, to look for these solutions?
These conical defects?
Yes. And if so, do you have an idea of where to look for accounting of all the light states, for looking for other solutions?
Okay, so for the first part, well, I mean, this idea that there might be solutions that might be non-singular, I found in the full theory, but which might be singular in the gravity description, look singular in the gravity description, I found quite striking and interesting. And one obvious candidate was to consider conical geometries, which are the simplest kind of defects. I mean, I had a vague hope that they might have something to do with these light states, but in any case, I independently thought it was an interesting thing to study, but it actually quite at various stages it didn't at all seem as if it was related, but it turned out to be fairly somewhat miraculously to actually agree with these light states. So it was a very pleasant surprise that it seemed to account for this class of primaries. About all the additional states, in some ways, perhaps bound states of these and perturbative states is probably sufficient to account for all the additional states. I wouldn't say this with 100% certainty. It's something Matthias and I are investigating now, but there's a reasonable chance that it might be so.
Is there a D-brane construction, like a decoupling limit of some D-brane bound state?
Of some D-brane?
Of some D-brane bound state that would lead to this gauge-Vesumino written models in the large N limit?
Oh, you mean sort of...
something similar to the D1, D5 construction, but for this particular CFT?
Yeah. It's one of the questions here about how to embed these things into string theory. I thought somewhere in this thing I had... maybe in the end I didn't put it in. About do they have to be embeddable in string theory and so on. So I don't know in this. I don't have any concrete idea about how to see an embedding precisely of this theory, but I suspect that this would be embeddable as a subsector of the D1, D5 system. Okay, let me say it slightly differently. At least maybe the lambda equal to 0 limit might be embeddable. Lambda equal to 0, lambda equal to 1 limit might be embeddable within say the D1, D5 system. For arbitrary lambda, I don't know. But again, if you want a decoupling limit which would give you precisely this sector, no additional states, because the D1, D5 system has a stringy degeneracy of states. That I have no idea how, but at least maybe you can, as a start, try to embed it within string theory, just like the twist-2 operators are some subsector of the full string spectrum.
Any other question? Okay, if not, let's thank Rajesh for the wonderful set of lectures.